Home philosophy questions beforehand is still not anywhere near guaranteed.
Well,
No.
we can start with our
Terrible.
last day in class. I'll see you on Tuesday. We'll start at 8:45, and I'll probably send an announcement, just a reminder that 8:45 time. I'll probably be in by then, but it just makes it rush earlier, and if student presentations are about 10 minutes, 10, 12 minutes, something like that. Then we will finish within an hour and a half, and it won't be overly long, but we'll get to see what different people are doing from talking to people about those. There's a lot of different things that are being done, so I think it'll be interesting to see the variety of things that grow out of this course. It's looked at a lot of different models. Thanks for being in the course. It's been fun for me. I enjoyed the questions and the interaction and working with a number of you to understand what's going on in these situations. And I think a lot of these problems came out of their consulting work or collaboration work or other studies that they did. There's a variety of randomized controlled trials and observational studies and things from different perspectives, and the use of statistical models is there to try to help learn things. And as you choose models that are appropriate for the data structure, the correlations, the type of measurements, they have sensitivities. Is it skew, or there outliers, or there correlations, or there other things that disturb the patterns or the things that you might observe and limit what you can learn and generalize to. And so you do a lot of checking and try different alternatives and think about different variables. And so I find that the process of applied statistics in that sense to be creative. You would like to have more variables and have more information and incorporate it somehow. And having been trained in statistical models, then there's in a lot of organizations, very few people who have more advanced statistical courses where they can think about models and think about alternatives and suggest changing things and check. So you have kind of a special role. And so in one of these big projects that might take a year and cost millions of dollars to do, like a big survey, there's this statistical expertise that's really needed at key points, at design, thinking about how you ask, set up the whole process to gather data so that it works out, and then the analysis, dealing with non-response, dealing with estimation, using variables in different ways, and so it can be I think it can be very interesting to get involved in a number of different applications. So for the course, right, you've seen the notice about evaluations. I hope we do put that in there. This course is every other year, but the type of comments that you make about what was good, what should be done differently, will inform other courses as well for future students at St. Michael's. So hopefully, I encourage you to do those, even if they're brief. If you have bigger comments, I do read all those. I don't see them until after I submit grades, so it's anonymous. I can't affect grades that way. Any particular questions you want to ask about or things? I did manage to post solutions or comments on the previous homework. I had let that lapse a little bit, but we don't have kind of a summary final. But if you're interested in any of those comments or results, you certainly could download them. It's a new world where you don't have to save paper anymore, but just electronic files. I've moved between different places, and it's always kind of an interesting process to move a few gigabytes worth of data, a few thousand files. It accumulates so quickly. And even for one of these courses, every lecture there's a half dozen files, and it just keeps growing and growing and growing. So, but any questions about it? Yeah.
So I guess this might not be specific to this course, but I was curious, are there any new statistics or data science courses in the works for future?
Very possibly, right? So, we're talking about the schedule for next year, right? And, we, at St. Michael's, this is the second year when there's actually courses designated as statistics. Right. So, as part of that process, we split, which was just probability statistics for the math majors, into a probability class and a mathematical statistics class. And the data science course is what's called introduction. It's really a 200 level course. Maybe it should be called, it's almost, it's a little bit more advanced with the programming aspect, because it's kind of, but anyway, there's that course and the computational data science course that used to be called CS202, but now it has the data science number. And so there is thought of adding a 300 or 400 level class in data science. So students who have taken more statistics, or at least taken the 202, 203, at least one of those two in data science, and another statistics class could take something that would be, there's rich material that's been there for a long time in statistical learning. Clustering, classification trees, using things where you don't assume so much statistical models, but really in the cross-validation perspective, where you would split your data, fit models, and then evaluate it on that. And some people do kind of a three-way split, where you kind of pick models with one set of data, and then you fit to estimate parameters with another part, and then you evaluate error by applying the estimated model to brand new data, and doing that repeatedly to get kind of a better. So there is thought about doing that, about exactly when to put that. So probably, if anything like that appears, to be next spring. Right? So, but it's teaching capacity, and also the number of students. So it hasn't happened immediately with this, because now there's more students that have gone through and are doing portions of statistics, data science, that offering a 300, 400 level class could get enough enrollment to make that happen. I hope it does. Something to think about. At another level, we have statistics 120, so we have an introductory statistics. The other courses require some calculus to be able to do some integrals or take a derivative. But there's a big demand, we think, for a second course, just statistical methods, non-calculus. Introductory statistics doesn't necessarily get through much of multiple regression, or it doesn't necessarily do two-way ANOVA or things like that, but a non-calculus version could very well be of interest. Students who have taken AP statistics come here, there's not much of a reason to retake 120, but they did the same material with 100 plus meetings in their high schools, where they could actually gather data and do stuff, versus a shorter period in time. So AP statistics certainly makes a lot of sense at the high school level for students who are ready for it. But then, should they jump into probability? Should they jump into mathematical statistics requiring calculus? For some of them, that's not really an optimal thing. So we might have statistics 2 at a non-calculus level. If they had that, then the data science courses might be a little bit, kind of make sure that they, there's different, always with, calculus has a kind of a pre-test, right, a placement test, kind of evaluation test to see if they got an A in high school calculus, do they really understand calculus? Some programs kind of, they, you've shown how to do a problem, and then you get kind of the very similar problem, and immediately after that, do you really know how to figure out from a whole group of problems how to do it? And but we don't really have that in statistics. We could do a placement course for statistics, but there's not much of a point of doing that if all we have is statistics 120, and then we have a smaller offering. Calculus is more gradiated, so. Yeah, so always thinking about that, of what we can teach. Another thing that's rolling out is junior seminar. And we plan to have a junior seminar in data science.
Okay, junior seminar.
Yeah.
Okay. But that wouldn't apply to juniors right now, would it?
Probably not, but, so part of the change of the core, right, is to have a junior seminar.
Right.
Right, so students in the future will have a course probably capped at 18 and have to do this junior seminar that involves some more writing and things like that. I mean, our classes like 351, 451 that I've taught have been, smaller than that. They often involve projects and data analysis where you write them. So it's not exactly the same. The idea of the junior seminars is that anybody can take them. No prerequisites. which kind of raises some other issues. How do you have a 300 level math course versus a data science course with no prerequisites? Right. So they're going to offer those. They have to offer a lot of junior seminars, like 23 junior seminars. There's a lot of faculty resources to teach those. So some existing courses would be called junior seminars at the first and kind of develop over time. And so we'll have to see how many sign up for that. We're thinking of offering one in data visualization. Right. So you have somebody who has no minimal. We don't think anybody who's never taken a statistics class, who's never done anything with data, would be particularly interested in jumping into a 300 level class like that. But they might. But so we're thinking is a class like that is students would have to be graded on an appropriate level. Junior data science, statistics, math students who come in, CS students who come in, could do the programming and could be graded based on that, whereas an art or English student or journalism student who wants to understand graphics from the point of view of writing, intelligent stories or education, right? That doesn't necessarily come with as much math stat background, but wants to have that element of it, could be graded on what they can do, right? And you just can't expect the same things. That's kind of a trick, right? That would go across fields too. So that would likely come. If that doesn't fill up, will people be allowed to take it? We're not sure. Right? I would think if it doesn't hit the 18 limit, many of them will, but if it doesn't hit the 18-person limit, would we allow anybody in? Would we allow one or two in extra based on permission? That's all kind of up in the air. And any other questions about it? So many students did the final homework, but because one homework was dropped and there's a lot of stuff going on, not everybody looked at the challenge or O-ring data that's in the book. And so I thought we'd look at that. Some of you have looked at it, and then there's more I can tell about that story going on. So these were the data that the book presented. There's different temperatures at which the space shuttles were launched. And there's something called an O-ring that is kind of a rubber ring that goes between the hydrogen, the liquid propulsion cells, the giant multi-story tanks carrying this liquid propulsion, and the engines, and you don't want those things to leak, because then you get the fuel leaking out and potentially, well, what it does, it can blow up. And so there's multiple O-rings, and they can fail in different ways. A catastrophic failure would just maybe break. They can also crack. So there's different definitions of what a failure is. And so there's the different temperatures that they were launched at on over time. Was there any failure? And there were some failures in terms of cracks and so on. This is arranged by time, temperature. See, there's also, the space shuttles were reused. That was the innovation. So you just don't shoot up a rocket and then have to rebuild everything from scratch. You have this airplane-like thing that you can land and then put it back on top of another rocket and reuse it. So you save billions of dollars doing that. But there were some failures at lower things. And then on a certain day, on January 28th, 1986, they were going to launch again. And it was 31 degrees. And they had to do an assessment that's colder than they ever launched. It's very unusual for Florida to be that cold. And so they had to decide, is it safe to launch in that temperature? And they thought it was, but then it blew up. Right. So there's data. The failure is how it was recorded, yes or no. For logistic regression, we change it to 1 or 0 there. Let me attach that. I always like to check to make sure my coding is doing what I think it's doing. And so, yes, failure is now 1, and no failure. There's just 24 there. And if you fit a logistic regression, you get a significant effect of temperature. As the temperature is going up, the odds ratio for having a failure is going up. So, as the temperature is going up, as the temperature is going down, the odds are going up because that's a negative. Right, so it's not, it's risky. You did a chi-square test comparing these. 1 minus p chi-square 5.944. With 1 degree of freedom is this p-value. So versus one that has no temperature versus the temperature it seems to do there. You can do confidence intervals for the temperatures, and if you exponentiate those, you get kind of the multiplier on the, this is 0.68 to almost up to 1. And if you plot temperature versus failure, you can see it a little bit better. Let me make this a little bigger over here. Plot, and that so it's decreasing. The range of the data we see is just 55 to 80. Up here at the warmer temperatures, there weren't many failures. You might jitter these because they're at temperatures, they're integers. There's not a big data set. If this was hundreds of data points, there'd be some overplotting you might deal with. But the data that we have where they were launching was back over here, right? So this is going to keep going up and be almost, almost for sure. You can do a prediction. The link is the linear one, right? We talked about this fit of 5.564 is on the linear scale, right? Logistic regression does that transformation, logit of p over 1 minus p, and then it's linear. So you can get the value on the linear scale, right? But we turn that into a probability. And if you have this as the beta 0 plus beta 1 times x value, the inverse transformation was the exponent of that, times 1 over the exponent of that, about 0.996, almost 100% sure that it's going to fail, right, with a chance then of catastrophic. You can also tell it to predict on the response, so transform it back to do it automatically. If you do that, it will give you, that estimate and a standard error for that. Right? Well, yeah, the standard error is quite small, but we can probably go plus or minus 0.9. Yeah, right. And that was kind of the problem there. There certainly seems to be a very high probability and not a very good idea. Now there's other things, right? This was over time, right? There was multiple measurements over time, so you could introduce maybe the space shuttle and different parts were aging. I don't know if they replaced the O-rings every single time, if they could reuse those. That might be a component that they replaced. But this is, so one analysis of this. Right? I think earlier on, they did kind of earlier in the book, they used these data for like a 2-sample comparison. Are the temperatures different between, failure or not? Well, you could do that as an observational study, right? To do that, but looking at the average temperatures by failure or not, while informative, is not probably as good as logistic regression, because logistic regression goes straight after the probabilities that you're interested in. But there's more to the story, actually. There's a journal, there's a journal. Other people have looked at these data because it was a very important issue. There's a journal called Statistica Sinica, which comes out of Taiwan. There it is. It's been a journal for 20 years or more. How far back it actually goes. Right, so 91, so approaching 20 years. And does some, specialized topics, and it has general articles, like general articles that are in this recent issue. Something for monitoring large-scale data streams, failure time data, different latent variables under right sense. So anyways, different things for use at different things, and many of them have, some of them are very mathematical, some of them have applications in mind, and then it has these special issues, and Bayesian environmental statistics, and so on. And back, in 2008, there's this one, modeling and predicting extrapolated probabilities with outlooks, was a topic. Where is it now? There it is. So you can get that, and this one's a free online journal, so you can do it, and this is the article. And so this focused on predicting, and the application it was used was the Space Shuttle Challenger disaster. Right? So that happened in '86, and so 20 years later, they're looking back. Could you have done anything different for predicting this? It's looking at that because that's a very hard problem. Different people said, well, if you had the data and analyzed it in different ways, even logistic regression, you're going to come up with a prediction. But it's a big extrapolation, right? So the question is there any sense in which you should believe in extrapolation so far? Right? This comes up in other problems, right? In biochemistry and things, it's called a low dose problem, right? A minimum detection level. So a lot of chemical assays, if there's a little bit of a hormone or a chemical or something that's in the blood or in the water or something, the test they have can't detect it. Right? It's going to be just a few parts per billion, and the test might come up negative, but that doesn't necessarily mean that it's really zero. It could be zero, but it could be below the sensitivity that the test can actually take. So you can kind of calibrate instruments when you have a certain concentration that's in there, right? You can measure the concentration accurately, but once it gets so low, it's just the science, the chemistry of it breaks down. So you could have all these low detections that are kind of below the prediction limit that the thing can do. So how do you deal with that? So this gross extrapolation beyond the range of observable data happens in other things too, right? And so the point of this article was to propose a way to handle this differently. And so it reviews some of the things, kind of EPA and things do a worst case analysis. If you can't detect it, maybe it's that. So it, looking at the probabilities of some transformation of the linear, this beta TXI is our linear, beta 0 plus beta 1x plus beta 2x written in matrices. And this is some transformation. Right? Could be logistic regression, other ones. And then they talk about, the inverse of that transformation is this link function, the linear part, right? So you can choose different distributions. We've used logistic, but there's a few others that can be used. And more discussion. So this had, it has a constraint, it proposes a new way to do this, to use it. Talks about a statistical inference procedure for evaluating that, and then does some comparisons. Right? And so it's about how should you do this? Right? Maybe you should use logistic, but there's a couple others, TOBIT or PROBIT, that get used in other areas for that. And so, it's a kind of a contingency table analysis. X are the different temperatures. And it's connected to that problem. And so then there's some transformations that they are doing there. And then they describe these as pessimistic, neutral, optimistic things. And that's a little bit vague to talk about. I don't really want to go in all the results, but as we go through this, we'll see some things so there's much of theory. But eventually it gets to the application, and we'll look at that. So it talks about the background of this. So they had a year look earlier at this 53 degrees, which is the lowest, I think, data set in there. They just found problems. It was 31 degrees when they were going to launch. And there were different discussions, right? And there were some engineers that said, no, you better wait, right, until it reaches up to 53 degrees, because at that below that point, we don't know what's going to happen. We don't have any actual data. And we've seen problems down to 53, so you better wait till at least that time, right? The managers didn't want a delay. They had some bench test data, right, conducted below 53 that showed no damage. And they had a higher launch at 75 degrees where there was some damage as well. So there could be damage whether it's hot or cold. There's some damage that can happen at any time. And so then they have these different sources of data that are not actual launches. And so it was the thing, each launch, instead of just actually having one observation, damage or not, there's actually 6 O-rings connecting these big liquid hydrogen tanks, rocket fuel, to the engine, and so then they can fail basically independently of one another, right? And so instead of actually having just 23 observations, you could have, 6 times as many. And so some people did different statistical analyses, so you could read those paper. Some did logistic regression. Some different probit or log, the different transformations. Right? And so what do the different transformations do? The different link functions, they produce different curves. Right? Here's all the observed data. And this is 81 minus the temperature. So 81 is the highest temperature. And up here is at 50 degrees minus that is the 31 where they actually wanted to launch. Right? So if you change the curve, which is going to fit down here, it has different impacts extrapolating. Right? And they're all very high. Right? And so expected number of incidents out of the 6 is 6 times the probability. Right? And so they're all expected to be damaged as you get up here. So having the actual data, not just failure or not, gives you, no failures out of 6, 1 failure out of 6, 2 failures out of 6 when it was at 53. And then, but the extrapolation is using the data in here to fit a curve. Well, then extrapolating the curve can go kind of more wild. I've seen this in different applications, like if you have data on, well, at GW, the people in the paleobiology had information on growth of, monkeys and chimpanzees and others over time. I mean, how do their body masses grow? How do their arms grow? How do their skulls grow? Well, they start out, small, and then they grow rapidly, and then it levels off. Right? But if you fit data in here, eventually it's going to come down, but if there's enough curvature around here, you can get something funny where it goes back up. And if you have a few individuals in there who are in their 20s or older, you get kind of these funny patterns way in the tails. And that's, it can be a little unsettling when it does something you don't think that's biologically plausible. You don't expect people to get bigger at the end of their lives in terms of many dimensions. Similarly up here, you're extrapolating, and so is this accurate at all? And yeah, there's some big, to me it looks overwhelming that there's a difficulty up here. The choice of these links makes some difference up here. And there's different things there. They do different things in inference, uncertainty about the parameter, uncertainty about the distribution, so there's some different approaches looked at different things, and they're trying to do confidence intervals, prediction intervals for failure, and they're quite wide in terms of that. And so anyway, they do their work here and come up with different probabilities, different tables for doing that, different likelihood ratios, and so on. 90% lower confidence bounds, different ways of calculating the probabilities, and then they talk about what would the engineers have. They have a way of incorporating that into that to try to, and I don't, without going into more detail. But anyway, so that's the nature of an article. So it's taken what was there before, this additional source of data, come up with a way of including it in the likelihood and the analysis, so you get estimates and then an idea about inference. Right? And right, we're gonna see if I want to say anything more about their work. Right? But then this was a discussion article. So at the end of this, then people go, there's some theory. It's a very long article with references. And then they start to have different discussions. And so some people in their discussions talk about assumptions or details that they've done in this. Do they think particular aspects are reasonable choices for modeling? Are there alternatives that they might have done? Have they really taken what the engineer said and the bench data does and done it in a reasonable way? So I wrote one of these discussions. I can find it. There I am. I was at Iowa State University at this time, so it was a while back. And so to me, one way of incorporating these extra data is to think like a Bayesian framework where the parameters we don't know, you can give probability distributions to them and come up with ways of then incorporating all the data. So we have the observations that are there, and if we're doing logistic regression, right, we're interested in the probabilities of the parameters, instead of beta 0, beta 1, I call them alpha and beta, given the data, and then some prior distribution, right? And if we had n observations from our real data, and then we had m observations from the test data that kind of equivalently expressed the opinion of the engineers and so on, we could simply add this little piece onto the likelihood there as a kind of a prior distribution involving these other sources of data and multiply them together. And then it looks just like a logistic regression probability function. Right? And then the question is, how do you summarize what is implied to be this distribution? There's Bayesian statistics that there'd be something in the denominator, kind of a normalizing constant to make this thing all probability. But, so you can either maximize this to find alpha and beta and get a prediction, but what some people do is try to sample values of alpha and beta from this distribution. Right? So if this is scaled the right way, this would be a probability distribution. And there's a sampling technique called Metropolis or Metropolis-Hastings sampling, where you can sample from something a distribution and then adjust what you're getting so it matches what the distribution that would be if you really could do it directly. Right? So there's a way to sample alpha and beta to express what that is. And this was something called this Metropolis algorithm. And so you'll get estimates of those parameters, and those estimates of the parameters then turn into estimates of probabilities. I think I took 50,000 samples to make sure no question that I'd sampled a lot, and then you can get inferences for those parameters. And so there was the 23 data sets, 6 O-rings each. There was some opinion about management versus the engineers about what would happen at 31 degrees. The engineers said, don't run it. The manager says, no, we can go ahead. Well, what does that translate into data? Right? I thought maybe, the engineers get 3 votes and the management gets 3 votes. It's like, well, treat it as kind of prior assessment that, put 3 counts successes at 31, whereas the management maybe is arguing, for 3, or the other way, or 3 successes, 3 failures. So, maybe 6 observations. Each launch gives you 6 observations. So if that one gives you 6 observations, it's kind of equivalent of 1 launch, kind of the value. There were bench test data on 50, 75, and 100 degrees. This was Florida, so you maybe be launching at 100-degree weather. And there was one failure around 50, but not at the others in the bench test data. So you had 4 additional O-rings. You could put 1 failure at 50 and then successes at the others. Now kind of looked like what data would come from an actual experiment. Right? And so if you just start with the original data, I'm not sure to make this bigger. We'll just leave it like that, right? You can estimate the coefficients with a kind of standard error, right? You can get predictions at 31 with standard errors, predictions at 53 with standard errors. You get confidence intervals for the different error probabilities. And data set's small. It's in a big extrapolation, so you do get pretty wide intervals. If you add in some data, that would be kind of 3 and 3, right? It changes some of the results to some degree, but these intervals for the probability of failure, 3 and 3 is more even, so it does pull it down, but it's still, the upper half or the upper end still is extremely high probabilities of failure. If you put in these other ones, this one had the 6, the prior 2 had 4 data points, which was just kind of the bench test data, translated into something like that, you get these high probabilities of errors, of failures. And if you put both sources in there, you can get other estimates. And so, in any case, you get some way of doing that, and that could have been done before they launched the shuttle, and you get very high probabilities of failure, and there'd still be a decision process, should they launch or not. But it's still, you're still extrapolating from data that's in you have some maybe hypothetical data based on opinion. So I thought, well, one area I worked in was mixture models, right? Maybe there's kind of one physical process going on at moderate temperatures and another physical process that kind of takes over once it gets cold, right? It's like water will remain water above 32 degrees, but after it hits 32, right, it starts to freeze. So there's kind of a change. So what you could see in terms of the performance of these things maybe is not constant overall temperatures. So a mixture model, right, says we don't have one probability model here. We have one alpha and one beta, but there's one at low temperatures and one at high temperatures, and what you see is a combination. Right? And both of these can be done with logistic regression, so you have these two sets of parameters and a proportion. There's ways with data to estimate that. Right? Basically, the algorithms go through the heuristic of filling in the data and saying, well, if these groups were in this group and this was in this group, we'd estimate alpha parameters for this group and parameters for this group. That, once we have the parameters, we get a likelihood. Right? And we also can get probabilities that individuals are in either group, right? Given their data. So the low temp, and so we can kind of classify after we have the parameters. Once they're classified, you can re-estimate the parameters. So it can go between classify them as group 1 or group 2, estimate parameters, and then go back and reclassify. And that iterates with something called an expectation maximization algorithm. So there's a specific algorithm in statistics that's key to missing data like that, like the classification data, that will find the values of alpha 1, beta 1, alpha 2, beta 2, and pi that maximize that likelihood. Right? And so you can do that. And to make those things work, there needs to be a prior, Bayesians would put a prior distribution on pi, on the probability of being in one group versus the other, so you can put a very vague prior on those. To make things work out, to kind of fix the mixture of components being non-empty and things, you could take a few cases and say, low versus high, right? And say the ones that are the lowest temperatures are kind of in the low group, and the ones that are in the high temperatures are in the high group, and then leave it up to the algorithm to try to decide where to split exactly. Is it better to split very low or very high? And so you can do the sampling and estimation, suggest this other model, and you get the two components. Component 1. So using you can then produce the same type of estimate. What's the probability differences based on the data? It changes the estimates a little bit, right? Points over 72 were assigned to component 1. So component 1 has a very low chance of probability. Those under 55 were assigned to component 2. And so these two are probably in those, and they have higher probabilities. So anyway, it tries to doing this would try to break the dependent, you're estimating data here and trying to extrapolate there. Instead of this, is trying to kind of break it at some point and say, well, you really should primarily use the lower data to just estimate. But so anyway, it's a different modeling approach. More could be done to probably assess goodness of fit between these two models. You really need the mixture to make this work out. And there was another source that I found in there. So anyway, it was just an alternative way to try, deal with a hard problem. And it's, if they had statisticians working for them who were doing data analysis and doing predictions, working with the engineers, trying to encode that data, maybe they would have come up with a stronger evidence-based, statistically based argument for not launching in 31-degree weather. I think they had a lot of pressure due to costs and things like that to get it launched. But anyway, I think there would have been more of a role for statistical analysis in that problem. And beyond what's in the book, where there's one observation per time period, there really were 6, plus these other potential sources of data. So in applied problems, often the role of the statistician is to ask, well, what other data do you have? How did you get that observation? How did you get that measurement? And find out what they've averaged together or what they've left out. And often that information can be useful. Right? I'm involved in some analyses for the Department of Veterans Administration on some of their survey data. And they have information in the database of 8.7 million veterans on many, many things. Gender, race, ethnicity, education levels, and things like that. And right now, they're not using that directly to design the survey. They're sampling by health markets and priority scores in terms of the veteran's health and the need for care. They're not explicitly controlling for all these other things. And so when they go to do analysis, after getting the data, you're subject to variability. You don't necessarily have a certain number of men and women, a certain number of minorities, and so on in the sample because you didn't control it. You're leaving it to chance. And so they very well could do something more complicated at the start, at the design phase, that could help with analysis later on. So there's a number of ways with that. Some ideas of knowing things about models like we've done in this class can help data collection to make it better, so when you do have to use the models, you're not having to make as many assumptions, or you're a little more comfortable with it. But anyway, I kind of wanted to finish up with that as kind of an interesting example that we've seen many things, but the more you know, the more things that you investigate and get experience with over time, the more things you can suggest and possibly come up with better models that give better conclusions that help make the world a better place for whatever you're working on. So, all right, so I'll see you on Tuesday. And a few of you have sent some things, and I'll try to send comments back. But keep sending things, and I'll make some suggestions. But otherwise, see you then. Yes. Great. And yes.
Oh, yeah.
The homework 10.
Can you teach me how to do that online function? I just says, equation are equal amount of rows. Like that. Which you don't get.
I'm not trying to do pre-test.
too. Have a good weekend.
If I made all the suggestions
Yes.
you gave, would you want to see it again, or do you think I'm all set?
I think you're pretty
Okay.
set for that, so.
Okay. Because I finished it last night and I just wasn't sure whether or not.
Yeah, I think that's fine.
Okay.
Yeah.
Thank you.
Yep. This is not yours, is it? This bottom?
No.